Statistics is like an onion, not because it is smelly or because it works really well in a slow cooker. No, it's because it has a lot of layers. And if you can just build up from the simple layers to the more complex layers, you'll have a much greater understanding of how to interpret all these medical statistics that get thrown your way. So our goals today are to walk along the statistical path from counts to risk ratios, slowly and deliberately and clearly along the way. We're going to demonstrate how denominators make all the difference in medical studies, and figuring out what the denominator is often really, really important. And we're going to introduce you to some jargon that just peppers all these papers and make it more understandable so that when you see it, you're familiar. To start us off, though, I am going to talk to you about what happens in my office in terms of drinking coffee. Let's imagine we set up a hidden camera in my office to figure out who's drinking all the coffee. Every time someone fills up a cup, click, we got them. Coffee, click, click, coffee, click. We do this day in, day out for weeks, months even. We collect so much data. We get 1,000 discrete episodes of coffee drinking. 600 cups are drunk by men, 400 by women. Would you conclude that men in my office drink more coffee than women? But I didn't tell you how many men are in my office. If there are 1,000 men and 1 woman, you'd better believe that the average woman in my office drinks more than the average man. But how much more? Well, we could compare the average cups per woman, 400, to the average cups per man, 1, and conclude that women in my office drink 400 times more coffee than men. Believe it or not, many medical studies work just like this. So, what happened in this coffee study? Okay, we started with something really simple, just a count. How many cups of coffee were being drunk by men and how many were being drunk by women? That's the bottom layer of the onion, okay? And then we added a layer on top of that. We asked ourselves, wait, we have to contextualize this a bit. How many men are in the office? How many women are in the office? And that gave us a ratio, okay? How many coffees per man? How many coffees per woman? But we didn't stop there. We added another layer. We compared those ratios to each other, right? How many times more coffee does the average woman drink than the average man? So we went from count to ratio to really what is a ratio of ratios. And what you're presented in a medical study very often is that ratio of ratios, which can be really hard to wrap your head around. But if you just peel back layer after layer after layer, you'll see underneath it all is just a simple count. So let's take a real-world example, perhaps a somewhat macabre real-world example. So this is the homicide rate in 2016 by state. Okay, so these are the top states for homicide. And you can see California in 2016 had 1,930 homicides, followed by Texas, Illinois, Pennsylvania, Georgia, and New York. So think for a second, what is missing from this data? Should we conclude that California is the most violent state in the union? Well, not necessarily, right? What's the denominator here? I'm just giving you the raw count. I'm not contextualizing what these counts mean. A relevant denominator here might be the population of the state, right? How many homicides are there per person, okay? This is a huge problem with many statistics you see on TV. So this is former Governor Mike Huckabee who was saying on Fox News, quote, "More white people have been shot by police officers this past year than minorities." And that was true. Governor Huckabee was making a true statement, but he was using that true statement to imply that assertions of racial bias in police activity are warrantless, when in fact he's missing an important denominator here, right? Which is that white people make up more of the population. And so the real question is, what percent of white people get shot by police officers versus what percent of non-white people get shot by police officers? So we really need to always ask ourselves, is the relevant denominator being included? So let's go back to our homicide rate state by state, but this time we're going to divide by the population in the state. So this is a sort of per capita homicide rate. And what you can see here is that California no longer appears in the top 10. In fact, Louisiana is the #1 state on a per capita basis for homicides in 2016. Congratulations, I guess. And the reason California had the largest raw count was simply because they had such a large population. Now, after we got that ratio, right, we want to compare ratios. Remember, medical studies are about ratios of ratios. So the next layer, if we were looking at the homicide data, is we might compare the rate of homicide in Louisiana to the rate in some place like Alaska. And we could say, okay, Louisiana had 70% more homicides than Alaska in 2016. Now, telling you what that exactly means and why that is the job of sociologists and other researchers. But what we've done is we took the counts, we changed the count into a ratio, and then we looked at a ratio of ratios, just step by step by step. Okay, let's do some medicine, all right? So this is how this looks in a medical study. This study is near and dear to my heart because I am a male physician and I happen to be married to a female physician. And this study came out in JAMA Internal Medicine in 2017, and it looked at the mortality rate, the death rate in the hospital among patients who are treated by male physicians like me versus female physicians like my wife. And if you just look at the raw counts, what you find is that in the population study, 2,029 deaths occurred among patients being cared for by female physicians compared to 4,549 deaths among patients being cared for by male physicians. But you're already saying, I can sort of see it in your eyes, right? You say, wait a second, what is the denominator here? That is a raw count. What's the relevant denominator? Well, that's the number of deaths. We want to know out of how many patients they were caring for. Okay, and so of course the researchers looked at this, and what they found, you can see down here, is that the percent of patients who had that outcome was 10.8% among the female physicians and 11.5% among the male physicians. Okay, so they took those counts, they divided by the number of patients total that the men and women were caring for, and they gave us a ratio for each group. But we don't want to stop there, right? My wife wants to know, are women better doctors than men, right? What is the comparison? How do we compare those two ratios? Well, sure enough, the study gives it to us right here. They give a risk difference. So in this case, they aren't dividing one by another, although they could. They just took the difference, and they showed that the average woman has 0.67% less deaths on her hospital service than a male physician. Now, caveat here, this was not a randomized trial. You weren't randomly assigned a male or a female physician, so there might be other differences besides just good doctoring to explain these differences, but nevertheless, it doesn't allow me to live down the shame I feel when my wife brings up this study. So I told you I was going to talk a little bit about jargon that you'll see in medical studies. So I just want to go through the big three here. If you know these three terms, you're covered for about 95% of studies in the medical literature. So you just need to know what they mean. So relative risk, these are all ratios of ratios, by the way. So it's just that final layer of the onion. Relative risk is defined as the risk in group A, let's say the risk in men, divided by the risk in women. Okay, or the risk in the treated group divided by the risk in the untreated group. So it's again, a ratio of ratios, right? Because it'll be like the risk of death out of the people who were untreated is part of it, and the risk of death among the people who were treated is part of it. So it's a ratio of ratios comparing the percent of people that experience an outcome in the population. So we went from counts to ratios of ratios. That's relative risk. The hazard ratio, that's another term you're going to see, is exactly the same, except instead of the risk in group A divided by the risk in group B, it's the rate in group A divided by the rate in group B. So let me give you an example. A risk might be something like your risk of death is 5% this year. That's fortunately very high, but I'm just making up numbers. Your risk of death is 5% this year. That's a risk. And we could say, oh, his risk of death is 2.5%. And so your relative risk is 2 because you're twice his risk. Okay. Hazard ratio rates say your risk of death is 2% per year. Okay, so do you hear that slight difference? It's not 2% this year, it's 2% per year, implying that there's some continuing analysis that's going to go on, right? We're going to follow you over time and we'll say, okay, you keep having this risk over time and it might happen at any given time. Very, very similar concepts, although the term hazard ratio sounds very scary. It really can be interpreted much like a relative risk. If someone says the hazard ratio was 2 in this group compared to this group, it basically means this group had twice the risk of death or whatever the bad outcome was, okay? And finally, odds ratio. Now, odds is also very similar to risk. I'll show you exactly what the difference is, but you'll see it very frequently. Again, interpret it mostly the same, all right? If the odds ratio is 2, it says basically that this group has twice the rate of death or twice the risk of death as the other group. And let me just get a little bit technical to show you the difference between risk and odds. So risk is simply the number of people that experience an event. If you look at the pie here on the left, the number of people who experience the event out of the total group. So we would say, 5 out of 100 people died. The risk is 5%, okay? The odds is almost the same, except it doesn't include the people that had the event in the pie. So if we were to, for example, if we were to say that 10 out of every 20 people get flu this year, the risk of flu would be 50%, but the odds of flu would be 10 to 10 or 1 to 1. So the odds of getting flu would be 1 to 1. Odds is weird. It's not intuitive. Why does it exist at all in medical statistics? It's because odds are important to gamblers, and gambling mathematicians are who derived all of the formulas that we use in medical statistics to this day, and the residual of that is you still get odds. Now, fortunately, odds and risk end up being very similar when the rate of outcome is pretty low. So look, if 10 out of 1,000 people get flu this year, the risk of flu is 1%, right? 10 out of 1,000. The odds of getting flu is 10 to 990, right? Because that 10 doesn't get stuck in the denominator when you're talking about odds, which comes out to 1.01%. Now, 1% and 1.01%, basically the same. So when the percentages are kind of low, the risk and the odds are very similar and can be interpreted very similarly. So I got a bit technical here. I apologize for that. But you'll see odds ratio a lot. Mostly think of it the same as relative risk, just that comparison of the risks across two groups. So our take-home points for today: most medical studies measure effects by a ratio of ratios. They go by different names. Don't get scared. Relative risk, hazard ratio, odds ratio can all be interpreted in exactly the same way. They all boil down to counts. Deep underneath, it's just someone clicking as cups of coffee are being drunk, okay? Make sure you have the right denominator. Always try to figure out what your denominator is when you're reading a medical study. Thanks a lot.